Hello, physical geographers. Hope everybody's getting acclimated to the course, getting used to where things are at, and find the material pretty interesting. One of the things that is very easy to relate to with physical geography is we kind of see it all around us. We see it in many things we do, activities, those kind of things. So, portraying Earth, we're beyond the introduction. We're going to talk about maps and globes, map scale, different types, projections, and properties. Properties being what aspects of each projection applies. We have different kinds of projections, cylindrical, so think of a marker, or think of a roll of quarters, planar, like a piece of paper, conic, like a cone, wrapping up a piece of paper tightly on one end and the other end being loosened. And then pseudo-cylindrical, which is cylindrical applied different ways, different tangent lines or um, different lines that we touch what we're modeling, which we'll talk about later. Map essentials. We use maps frequently to communicate and to direct us. Isolines, so values are the same and portraying three-dimensional landscapes. Okay, next we have GNSS. So now we have, as of the last 30 years, a definite improvement last 30 years with cooperation from international groups and agencies, especially the last 50 years it's existed. Even further, we have the Global Navigation Satellite System where we can use triangulation to locate things. So we've all heard of GPS, and now we can do some triangulation with our phones. As accurate remote sensing, so it can be aerial photographs, planes, helicopters, planes flying very high up in the jet stream, thermal, visible light, multispectral remote sensing, so different bands. And then we have geographic information systems, so overlay analysis, GIS, and decision making. And we see like different routing type applications we can use through the web or quickly find radar or weather. And these are tools of a geographer, really. So we look at maps and globes, and we talk about geography, which is the Earth and mapping it. And really we see the globe as being the most accurate and symbolic tool we can use to show the detail of the Earth's surface. Maps are a flat representation of Earth, so they'll have some distortion. They portray spatial relationships in 2 dimensions. So you're really taking 3 dimensions and putting it into 2. So it makes sense there's some distortion. And selecting specific features really kind of gives maps a theme. So maps show 4 basic properties of an area: size, shape, distance, direction. So we'll go into detail about those, what works well. Thematic we talked about. Thematic, we could have a highway map to see which major interstates we need to take, or we could have trail map that shows where certain waterways are, and so forth. Map scale, really we show different things through different ways. We could have a graphic map scale, fractional, so 1 inch equals 24,000 inches, or 1 inch equals 24,000 feet, which is what we see in USGS quads. Verbal map scale, so just communicating, it's this far. Graphic map scale, so we somehow show what the actual symbol is as far as what's mapped on a 2D surface. It could be hard copy, could be electronic, and what the real world is. So that conveys a difference. Large scale map shows a small area. Small scale map shows a large area. Kind of easy way to remember that. Map projections, so shape, relative area, distance, direction, we talked about before. So usually we only see 1 of those very accurate. Sometimes we see 2 of those accurate, which we'll go into in detail. And cartographers essentially can control what they use based on the projection source data on what works well and what doesn't. So cartographers being the producers of the map to make it friendly and readable and presentable and aesthetically pleasing. So equivalent map projection, equal area size ratios are maintained. So we keep the area of Colorado or the area of Kansas, we keep it so the area is the same. Conformal, we maintain the shape. Distorts the area, though, is the cost, so it's not like equivalent map projection or equal area. Once again, we talk about trade-offs. And compromise is a map projection that's neither equivalent or conformal. So it's kind of a negotiation of the two, which we talked about in our 4 map properties, projection properties, that sometimes we can keep 2. So here's an example of that. More map projections. Cylindrical, so here's our roll of quarters or our marker, and we see where it touches the earth on the sides. The widest part where it touches is a great circle route. Great circle routes always travel along the widest part of the earth, and they're used to measure what the actual distance is and consider the curvature of the earth. Mercator projection, same kind of thing, conformal cylindrical, where we actually maintain the shape of the earth. So it is a negotiation of trying to keep 2 things. The planar projections. Frequently we see this used around the poles, the North and the South Pole having Antarctica, which is has huge interest in the international community, both from ecosystems, because there are species that exist there nowhere else, plus in addition to using the planar projections, there's many countries that have interests and a stake and actually legal rights to Antarctica for essentially climate change. It's one of the few places we could actually core the ice that has been frozen over millions of years to detect what gases were in the environment many millions of years ago. So the international community has, many countries have interest in Antarctica, so it's great to use the projection, and it's all centered around the point at the South Pole, and also it helps us map the rare species. Iconic projections, these are used in very local systems, so if you go and buy a house or a property interest, or you look at a land title survey, they'll frequently try to keep those very accurate because of the legal implications, and they will be surveyed in a local conic coordinate system, which in the United States, that's all organized by state plane. Most state plane coordinate zones are conic. Some are UTM. Pseudo-cylindrical projection. So it's conformal and equivalent. Once again, another negotiation. Where is it most accurate? It's most accurate around the standard parallel, but it tries to maintain shape by pulling it in where the distortion is. Map components. Data source, location, direction, scale, legend, title, date, and then we talked about projection type, which has really been our focus. ISO line, so we have a bunch of points that have the same values, so we draw a line through it. It's like a contour line, but essentially could have different values. What values? Isotherms, values of equal temperature, precipitation, magnetic declination, atmospheric pressure with the isobars. We can overlay that, draw that, and use it as a layer and overlay it. We could also relay DEMs, so showing different types of models. In the Geography 105 class, we essentially, in the section that I teach, we essentially run through Mount Rushmore and show where the DEMs are created on Google Earth and Google Maps. GNSS, where the cooperation we talked about in the 4th slide. GPS is where 3 or more satellites, usually 4 or more, triangulate or come up with the same location on Earth to figure out where accurate is, and then it's transmitted to a specific tower. WAAS is essentially using a base station to correct that, so we're not traveling as far to figure out the distance and triangulate where that exact position is. So it's much more accurate. So basically we use something that's much closer to resolve or reconcile where those distances are between the 3 or 4 or more satellites. Remote sensing, airplane, satellite imagery, it's used for that. Orthophoto maps, frequently from aerial, we use those to get our really accurate local information used for tax-based mapping, or also known as cadastral mapping, and other sources. And we also use light and infrared sensing. We have several different ways, along with thermal sensing, to determine what's in our environment as we model the Earth and our world. In multispectral, we can basically use different bands in the electromagnetic spectrum. For instance, TM Landsat Band 4 is used in precision agriculture to identify where the best vegetation is, and then depending on the vegetation, nitrogen, phosphorus, or potassium are applied to yield the crops. And that's a big deal in the United States, as 90% of the world's crops are grown in the United States, and we heavily use that technology. Radar, sonar, so radio detection, sound, light, but any sense we have. And then GIS, dear to my heart, create maps, searchable libraries of spatial data, and have location coordinates linked to a variety of data. Data has come a long ways from when I started this 30 years ago. GIS, we can have wetlands, floodplains, survey control, remotely sense data from all the sensory type things we mentioned. You can overlay it, query it, and do some really powerful things. So the tools of a geographer, talked about different types of satellite information, GIS applications, different sources of maps, imagery, all those types of things. We can do careful designs to make maps that we can use to model and display output of our physical world through geography. Thanks for staying in tune. This is really an interesting chapter, and I think it's a nice lead-in to the various areas we dig in further in this book. Stay tuned.